Hello, my name is Pratap, and today in this poster I shall discuss how can we think of designing new materials towards enhanced room temperature photovoltaic effect, particularly ferroelectric material. And I shall also demonstrate how bismuth and Fe world of BTO can be promising in this regard. So as you know, photovoltaic effect is the direct conversion of sunlight into electricity, and it is regarded as one of the most promising alternative clean energy sources. However, the efficiency of such photovoltaic devices is limited, what is called the Shockley-Poisson limit. And as you see, popular semiconductor materials has efficiency less than this predicted limit. However, it is interesting to note that recently the photovoltaic efficiency obtained from a ferroelectric barium titan crystal exceeds this limit. This clearly exemplifies the promise of using an alternate ferroelectric material over the usual semiconductor ones. And this is achieved because the photovoltaic mechanism in ferroelectric material is somehow different. Here, the electron hole pairs are separated by the internal electric field induced by this spontaneous ferroelectric dipoles, which are spread over the entire sample, not unlike in usual PN junction devices where the electric field is restricted in extremely small junction region. However, we have to note that the band gap of ferroelectric barium titanate resides in the ultraviolet region. So to obtain photovoltaic effect, we have to tune this band gap of barium titanate towards the solar spectrum region where optimum efficiency is expected. Not only you have to tune the band gap, we also have to sustain large ferroelectric polarization for efficient electron hole pair separation and simultaneously higher conductivity for large short circuit current. However, the optimization of all these three physical properties in a material is extremely counterintuitive, thus extremely challenging to realize in a material. And for that, we need proper material designing. And in this regard, we have designed bismuth and iron doped barium titanate. Where iron concentration is though fixed, we have progressively varied bismuth concentration, and we immediately see systematic tuning of conductivity, optical band gap, and ferroelectric polarization. Now, from the triangular requirement of optimization of the desired physical properties, we see that X is equal to 0 to compound seems to have better optimized compound in this series. Then we immediately test photovoltaic measurements on this in this geometry on this X is equal to 0 to compound, and we see that before polling the sample there is no significant photovoltage. However, upon polling this there is a significant generation of photovoltage upon light illumination, and as the polling strength field strength increases, the generated photovoltage strength also increases. It is interesting to note when we do the similar measurement on an almost paraelectric compound, we see even after polling, we hardly see any response of photovoltaic effect, which is though observed in ferroelectric materials. So this also clearly exemplifies the role of ferroelectricity towards such kind of photovoltaic effect. Next, we have plotted the variation of band gap, polarization, and conductivity on different representative samples, and we find that X is equal to 0 to compounds exhibits largest photovoltage because it has this physical properties, band gap, polarization, and conductivity in right appropriate amount. Thus, we see that X is equal to 0 to is extremely promising compound, and we have also seen that on the background of Shockley-Poisson limit, X is equal to 0 to resides on the optimum region where maximum efficiency is expected. Thus, we are extremely exciting to see the photovoltaic response on a craftily designed thin film devices of this compound, and we have already started working in this directions. We have also found the controlling parameters behind tuning of these physical properties like band gap, polarization, and conductivity. We found that jointular distortions tuned the optical band gap, tetragonality tunes the polarization, and oxygen vacancy helps in controlling the conductivity. Though due to time limit, I have not been able to discuss the role of all these parameters in detail. So I'm sorry for that, and thank you all for listening.